A study at The Ohio State University asked 16 college students to drink a randomly selected number of beers. 30 minutes later, a police officer tested their blood alcohol content, and here's the data that we came up with. So the question is, first, can we come up with a predictor to guess how much blood alcohol content a guy would have if he, say, drank 5 beers, if that's the only information we had? Yes, we might prefer to know some other information. Is it a boy or a girl? What type of beer? All this other stuff that either is relevant or you think may be relevant. But if this is all we have, can we come up with an equation that makes a prediction? So how would I come up with that equation? What is it that I need to do? Do linear regression, exactly. So stat calc number 8, and I'm going to store it into y1. So there's my equation. If I looked at a graph, I could graph plot 1 with that equation on there, and I get something that looks like this. There's my y-hat line. The whole point of linear regression is to make predictions. That's why I'm doing it. But I also know that all I tested here were 16 students. So do you think that this line is the true relationship between drinks that a college student would have in his blood alcohol content? No, it's going to be close to the truth though, right? As long as these students are randomly selected or represent randomly selected college students. It might not apply to adults. It might not apply to children. But whether or not it would apply to college students, as long as these well represent college students, I'd be okay with that. So do you think that there really is a positive relationship here? Or do you think that these 16 just lead us to believe that? How do I test to see if there really is a positive relationship? All right, so if I turned on my diagnostics, so I heard R. So let's check this real quick. R squared is about 80%, telling me that 80% of the change in blood alcohol content from one number of beers to the next number of beers, 80% of that change could have been anticipated by using this line. But do you think that it's truly that there is truly a relationship here? That's when we do the LinReg t-test. It's to see if there's a true linear relationship. Now we did this, and I'm going to skip to some computer output. I typed this stuff into Minitab, and I got this equation, or this data, out of Minitab. Unfortunately for you, I got tired of typing, and so I didn't type in the two things that have stars on them, the T and the P in the column or in the row of beers. So how could I figure out T and P? What's the formula for T? Good, it's B divided by SEB. Sometimes that's called the T ratio. Some of you guys may want to write B minus beta divided by SEB, but we're hypothesizing beta to be 0. So in order to figure out this value right here, I'm going to take this number and divide it by this number. So let's go here and see, this is 0.017964 divided by 0.002402. That's my t-test statistics. Now in this particular example, since you have the data in your calculator, you could do LinReg t-test. And when you did LinReg t-test, that would give you that t-test statistic. But if I didn't give you the data, like in second period, I didn't show them the data, I just showed them this, you have no option except for to divide those two things. Now using your brain and nothing else, what do you think the p-value is going to be with that t-test statistic? Really small. Okay, we've got a really big test statistic, so I got a really small p-value. If you were using your calculator, you could do something like this, TCDF of a lower bound, upper bound, degree of freedom. What are the degrees of freedom? 14, because there were 16 college students, so n minus 2. And my p-value, of course, is something really, really small. So I reject HO in favor of HA, and I now think that there is a positive relationship between the number of beers and the amount of blood alcohol content. Now we've got some conditions we talked about yesterday. What were the conditions? Okay, so I need these college students to represent the group. Okay, what else? We need a true linear relationship. So how do I check that? Great. So let's see. Here's the residual plot. I think. See, in plot 2, I have resids. Sorry, that's the histogram of the residuals. What is this going to tell me? Something about normality. So, I don't know. This isn't great. This isn't great. I'm a little concerned about that, but I'm not overly concerned about that. But I need my residuals to be normal because the way that's stated is the points need to be normally distributed around the line. In other words, when I looked at this, most of my points need to be close to the line, a few of them a little further away, and even fewer of them further away than that. But the residual plot here, I guess I've got in plot 3. So let's look at the residual plot. And I'm looking for a pattern. Ignore this, that's just my y hat line. Do you see a pattern going on in here? Not really, so linear seems to be like a good idea. What else can I look at here? I need sigma to be constant. Now I don't know sigma, but I do know S, and S is the spread of the points from the line. Does it appear that the points are getting more or less spread out as my X changes? Not really, so I'm okay with that one too. So those are the conditions that I need to check. Now that we've kind of done all that, what if there's a fella, we'll call him Steve because I think that's what the book calls him, and Steve drinks 5 beers. What do you predict his BAC will be 30 minutes later? Try it. He has 5 beers, 30 minutes later, what do you think his BAC is going to be? So since we've got the equation in Y1, an easy way to do it is to just plug that in like such, and that's the prediction. Now what if Steve's friend Bob also drank 5 beers? What do you predict his blood alcohol content's going to be? We predict the same thing. But we're also slightly bothered by that because while we're going to predict the same thing, we know there's like no way they're actually going to have the same blood alcohol content, right? All right, so if I was looking at my graph, another way I could do this is if I looked at the original graph, and this is sort of the Algebra 1 idea, is that down here on the bottom, I could go to where 5 is, and then I could go up and over, and that would be my predicted amount. But I also know that that value is probably not right. A better guess would be some sort of interval around that. So I don't necessarily know that he's going to get 0.077, but I think it'll be 0.077 plus or minus a little bit. That's the idea of an interval. I'm pretty sure it'll be within some interval that's centered around 0.077. Now let's further the example here. Suppose that all of you guys went out and had 5 beers when you were of age, and 30 minutes after the fact, we measured your blood alcohol content. Where do you suppose the average blood alcohol content for all of you will be? I would still guess the 0.077, and I think it would be really close to that. So do you think that the average of all of you guys would be closer to 0.077 than just Steve, or do you think Steve's is probably closer? Probably the average, right? And so this gives us 2 different kinds of intervals. One of them is called a confidence interval, and one of them is called a prediction interval. The confidence interval is the guess for the average. The prediction interval is the guess for the particular person. Now, both intervals use the same kind of idea that we've used for all of our intervals. Namely, the formula is the estimate plus or minus a critical value times the standard error of the estimate. So in this case, when I make an estimate, what am I estimating Steve's blood alcohol content to be? the 0.077. What am I estimating our average blood alcohol content to be? 0.077, same thing. All right, well, how about the critical value? What the critical value is just the T-star, right? How will the T-star for Steve compare to the T-star for all of us? Same T-star. Now, this bothered a few people earlier in the day, so let me talk about it for a second. T-star, or the t-test statistic, comes into play with the degrees of freedom. And it comes into play with degrees of freedom because the original data is not quite right. The original data is not all the data. And so I've got a little bit of error that's introduced by just using some data instead of all the data. So even though Steve is only one person and we're a whole bunch of people, the degrees of freedom comes into play with the number of data points that I used to make this line. That's where the error comes from, is because this line isn't quite right because it doesn't include everybody drinking 5 beers in their blood alcohol content, and it's only 16 college students. If this line included everybody, it would be the true line. But it's not. It's just a guess. I think the true line's close to there. That's where the degrees of freedom comes from, and that's why Steve and the class have the same T-star, because the T-star came from the data, not from what I'm sticking into it now. So the difference then, obviously, falls into this part. The standard error of the estimate for Steve is different than the standard error of the estimate for the class. From your worksheets the other day, the last two formulas are written here on there. One of them is for the confidence interval and one's the prediction interval. Those are both the standard errors. Those are both the parts that are going to go here at the very end of this formula. So examining these two formulas, what's the difference between the two formulas? There's a 1 plus. Now, we're not going to worry at all about where the 1 plus came from or why it's 1 instead of some other number or anything like that. We're not going to worry about it. There's a reason. Who cares what the reason is? But we do know that when we stick that 1 plus in there, the standard error for the prediction interval, this value is going to be bigger than the value for this, right? A bigger value is going to therefore make the plus or minus bigger, making the prediction interval wider. The prediction interval, the guess for a particular person, is wider than the guess for a group or a guess for an average. The true average is going to be closer to that prediction than the prediction interval will be, which is for a particular person. So I continued with the Minitab output. And it gave me this. So when I stuck the information into Minitab, it gave me this output. The fit, that's where the point, where the data point fits the line. That's the 0.077. Standard deviation of the fit is that standard error business. Now, which one of these intervals applies to Steve? I'm 95% confident that Steve's blood alcohol content will be between this one right here. I'm pretty sure Steve's number is in that interval. I'm pretty sure the true average is between 0.066 and 0.088. That's the confidence interval. Now on your test, you're going to be expected to understand the difference between confidence interval and prediction intervals. You're going to need to be able to identify which one to use, especially given the output. You're not going to have to go through the formulas off of this sheet. However, I don't really think the formulas are that hard. So look at the formulas for a second and see if you think part of them are hard. What's X star? That's a great question. X star is that magic number I stuck in. I said, what if Steve drank 5 beers? So X star for this problem is 5. It's whatever number you're sticking in, because where did the 5 come from? I don't know. I made it up. Steve drank 5 beers. Okay, so that's where the 5 comes from. So X star is 5. So that's a number. X bar is a number. You get X bar by looking at one var stats. You can square it. You can do sums and lists just like we've done before. It's really not that hard. This S at the beginning, that's the same S we did yesterday and the day before. It may be annoying. I'll grant you that. It may take you a few minutes, but it's not actually difficult provided that the formula is in front of you. Except that I'm not going to make you do it. You just have to know that the prediction interval is wider. The prediction interval goes with a particular person. Predictions for particular people. Confidence intervals are for the true average. And that's the rest of chapter 14, talking about confidence intervals and prediction intervals. And from there, we should be good to go on everything else.